This is the third in these series of lectures, and I'm sorry it's taking so long. I will take 10 slides just to review what we've seen. We have shown that active cold fusion, or lattice-assisted nuclear reaction components, when electrically driven, give off a signal at the deuterium line, which is at 327, well, deuterium line 32738, but very close to the deuterium line, as an electromagnetic emission. We have shown you that outside of a Faraday cage, a Fabry-Perot box, we get a very high Q signal, which is about 10 to the 8th. And within the Faraday cage and Fabry-Perot structure, we get a blazing signal. And here you see the galactic lines. Time goes in this direction. These are time labels. It's about 15 minutes. And this is an instantaneous output showing the peaks that we see over approximately 30 kilohertz at the 327 megahertz region. I then showed the second day that when we increase the applied electric voltage to these components, they separate out into a series of side bands. This is at 2 volts. Here we're putting on about 20 volts. All of a sudden, these other bands appear. And when we look at these bands, let me go back one. What I'm going to show you is these are fairly symmetric. I'm going to take this region from here, flip it around. And so the thing that's at the farthest, it will be, by resonance broadening, the site that's closest to the active site. When we take our model based on resonance broadening, which goes as a 1 over r cubed fall off, we see that there's a very close match for these lines for the second, third, and fourth positions, although something strange has appeared at the second position, which is either an interaction with a ferro or paramagnetic material or some interaction with one of these other sites. This shows the previous 2 talks that atomic deuterium as a free radical is the precursor to making helium-4, and that when we up the voltage and create these super hyperfine structures, which are the side bands of the hyperfine line, it indicates that this occurs in a face-centered cubic vacancy, which we first thought was surely palladium, but in fact, as an alternate hypothesis, could be a rhombic phase, which is zirconium oxide, and we're not really sure which it is yet. So today I'm going to show you, I also showed, by the way, that we also see these deuterium lines for the aqueous system, where we use ordinary water, which has deuterium in it, with nickel. And we use what we call the mother of all cathodes. And when we do that, we get, for example, here it's off, though it had been running for a while. We find that when we get the deuterium line and we turn off the applied electric field, there's a fall off of 1 exponential every 3 or 4 minutes, and finally it goes to 0. So here we're driving it at the peak optimal operating point. This is just on the other side of it. And when we look at these sideband structures, we're looking at nickel in ordinary water now. This is approximately a megahertz in width, much wider than the zirconium materials. We see a number of bands, and what really blew me away is, look here, it's pulsing. And that is interesting because it's not seen anything anywhere else. We've looked everywhere. We've looked at galactic lines. We've looked at the outputs of the active cold fusion cells, and we've never seen pulsing except for here. And I'm going to need your help to explain what it is. Just as a quick review, these are from the hyperfine lines, which is the interaction of the deuteron nucleus with the electron spin around it. For hydrogen itself, this is the 21 centimeter wavelength, 1.4 gigahertz, and this drops to 327. For the deuteron, it's used in radio astronomy, and our biggest problem is that we have a very large input from the center of the Milky Way, and although we initially used an Earth to shield it, you really want to use a Faraday cage The pulsatile lines that I'm going to show you were obtained from this device, which had been run at Lincoln Lab at MIT for many months. And during that time, they found that the deuterons had a loss of 43%. And this work was kept covered up until I published it at ICCF21. The reason they weren't interested, although to me it's just a knockout, because Mel Miles and others had showed that we make de novo helium-4, and gosh, here we see it's from a could we fix that? It's from a loss of the total deuterium content. I need you to fix the slides. Oh, I got it back. Okay, thank you. The reason they didn't publish it was the initial study was looking for hydrinos, and they found no hydrinos, so they thought this was of no interest. The other thing I showed at ICCF21 is that the dry components, the nanors, as well as the aqueous systems really have two states. They are completely distinguishable. Here you can see it. This is the ohmic control. This is the output heat. This is hydrogen generation. And here we have the active state, much less electrical input, massive amount of heat production. This device gives as much as 70 watts excess power output. And here we can flip the state where now we're getting almost no excess heat out in just hydrogen evolution. A clear demonstration that there's two states, and if you want an active system, you've got to make sure you understand it so you can drive it at the right state. Okay, so in our methods, as I told you, what we do is we have a Fabry-Perot structure. This direction is 1/2 wavelength. You've got to have at least a half wavelength to do it. We put an antenna inside, and here's our antenna, and here's the device, and this is the half wavelength right here. We don't have to talk about the antenna. We did it before. The really important thing is if you want to see stuff, you've got to do a really good ground. We talked about it, go back, and if you do the ground and do it well, you'll have a clean region that you can examine the output. We don't have to talk about this except for the fact that you need to know this is very close to what we do in calorimetry, except that here we talk about luminosity in terms of joules per second. And it's just slightly different terms, but it really is microcalorimetry. And you're looking at the rate of heat rise on the antenna from this. The advantage of doing this over what we do in calorimetry is that the longer we measure, the less the noise. And let's look at the results. So here we have, this is really ordinary water, so it's mainly H2O, but there is deuterons in it as well. We have 1/2 mile of nickel. There's a massive amount of platinum, and only MIT could have put this together. And as a result, here's the signal, and then we pull out the side bands, and we have this pulsatile line. And what's really interesting is we have matching pulsatile lines. It appears that something is going on here. Here's the pulsatile line. It really is. I mean, what could it be? This is a unique, super hyperfine line that we see with periods of minutes. It's unlike anything we've examined over 2 years on Earth or from space, and it only occurs when we have an active cold fusion system. One of the things I'm trying to do is to build a movie of it, because if we're having pulsing going from one line to another, can we make some kind of movie that shows what's going on? And I did not have time to finish that before I came here. See, for example, here, if you look at the pulsing line, when it drops, other ones rise. So here's the pulse, 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 pulse. So I started looking at other lines, line 1, line 3, and again, this is why we need a movie. It appears that there's some sort of movement. Is it a quantum movement? Is it a mass energy movement? But we have to ask something first. Could it be mode locking? Because that's, I don't know how many of you know about mode locking, so let's talk about it. Mode locking is a laser technique for making ultra-short light pulses, picoseconds to femtoseconds. It's a result of enforced coherence between multiple axial modes in a laser. Now remember, a laser, when you have it, has many, many half wavelengths. Our device only has a single wavelength, and we'll talk about that, in fact, is why this is not mode locking, but I've got to go through this with you. So in mode locking, what happens is the pulses arise as a train, the laser becomes phase locked or mode locked, and then you see single pulses come out. I first made one of these with Herman House, I think it was 1967, and our assignment at MIT in the undergraduate lab, he said, make a mode locked laser, and that's where we first did it. Now, in electrical engineering, the goal has been over 6 decades making shorter and shorter pulses. But this is probably not mode locking, because in laser mode locking, the cavity is hundreds of wavelengths. And so in that case, they can interfere. They can superimpose and create these coherences. Whereas with us, there's only a single mode. There's only a half wavelength. You can't get interaction between multiple modes because we have only one. There's another reason that it cannot be mode locking, and it has to do with the transit time. The transit times in mode locking is equal to twice the length of the cavity divided by the speed of light, and these pulses are minutes. That's the second reason. Third reason it can't be mode locking is the shape. In mode locking, the pulses have a Gaussian shape, but not always. By contrast, these appear as step functions, or something close to it. Now, that could be a result of the fact of the qualitative analysis of our intensity. We don't have a completely linear system yet, but it seems unlikely because the radio frequency examined does not significantly change. So what then is it? You can see it. You can see that it goes from one to the other. I wonder if it's an energy-matter movement within the lattice itself. Over 30 years, we have absolutely active cold fusion systems. There's no question about it. So how do these interrelate? Could they be Deuterium energy mass movements and redistributions between the lattice to create the active state? Could it be? I mean, there are many models for looking at this. We've got Bose-Einstein condensates. We've got ion band states. There's quasi-particles. It could be one of them, because a model is just a way of looking and trying to describe what we see. The other possibility is Deuterium noted that the recognition of coherence in the self-sustained masers longitudinal modes might be related to these. And also we saw a paper on Tuesday where there was a discussion where if you have changes in amplitudes, this may herald the loss of the Coulomb barrier. And I didn't have time to add that to this. Anyway, do not give up. Please, if you can figure out a way to give me an idea of what to look at or do this yourself, I'll give you whatever thing you need. And one other point. I've only looked at the deuterium line. There may be other lines to look at, hydroxyl OD dot, I don't know. But there's a wide number of frequencies that are available in this protected region of space, the electromagnetic space, where you could look. Anyway, thank you.
Thank you.
Mitch, I just realized when you put that up there, there's 3 magnetic fields, rather strong. You've got the Earth cutting. You're not in an iron box, so you've got the Earth's magnetic field. You have the solenoidal magnetic field, and then you have nickel's ferromagnetism, and you might have a precession, and something simple like that.
Would you expect it to be with a frequency of minutes? We'd have to work that out.
Who knows? I have no clue. If you put it in an iron box, we might be able to shut it down.
That's a good idea. Thank you. Dennis.
Another question.
Hi, I was wondering what kind of spectrum analyzer you were using for your RF.
Oh, good point. Software-defined radios are available on eBay, anywhere between a range of about $60 and several hundred. And we built multiples of it. I buy several of them now. Our latest thing is trying to use multiple software-defined radios to look at different frequencies at the same time. Easily available.
Thank you.
Yes, please.
I was thinking about, you talk about the movie, some sort of, if you take a spectrometer in with the time component, so you can see, evolution of the signal in time, and that gives you, the 3D dimensional information. So you can see maybe something else that can bring the third dimension in time.
Exactly. That's why we're trying to do the movie. And the question was whether to make it like Edison's original device, rotating around, or doing multiple JPEGs and have them come on in time. I just haven't had time to finish it before this meeting, but that's a good point.
Is it possible that the signal you're seeing is from outside of your Faraday boxes? Because it's a very low frequency signal. Maybe it's something that isn't blocked by the double Faraday arrangement.
I think that's unlikely because I don't think anything can get in. When we end up coupling it by a ribbon cable to 8 feet into the ground, all of the other signals go away. And it's a dual Faraday cage you'd have to get through.
Yes.
It could be from within. I just don't know yet.
Well, if it is a diffusion effect, you should be sensitive to temperature. Can you change the temperature of your sample one way or another to see what happens, if the frequency changes or not?
That's a good idea.
Yeah.
Put an extra heater in it or something, whatever.
I'll have that by next time.
Okay, thank you.